be bought out again anytime soon. But thanks, like Don said, my name is Chris Papineau. The title of the presentation today, and it is session 421, is Performance Engineering Parables. Yes, I am from Denver. No, don't talk to me about the Denver Broncos right now. You'll put me in a very bad mood. Talk about the Patriots, though. It's my other team. That'll put me in a better mood. So one thing I ask is for questions to be saved till the end, please. I've got a lot of material. I'd really like to cover it. So hopefully you brought something to write with. If not, the back of your hand will work really good if you want to write down notes. Also, I won't evaporate and disappear after the presentation. I can hang around out in the hall if I said something that really somebody thinks, gee, Chris, you're all wet, type of thing. I can talk about those afterwards. However, we do have a brief audience participation part of this at the very beginning, and that's now. If everybody could repeat what I say. I promise to be different. I promise to be unique. I promise not to repeat things other people say. Now the point here is, a lot of this today is performance engineering parables. A parable is a story that stands for something else, okay? It's an analogy. The way to describe these things to people who think differently, if you want to buck the system, with people above you in the food chain, so to speak, that make the decisions, performance is one of those concepts that's best described and communicated to people who are, shall we say, non-technical through analogy. I like to do that. I've been to a number of other sessions here already where that has been the case, that it seems to be a very common discovery, is the use of analogy from something outside of IT to describe IT concepts. Performance engineering is, in my opinion, one of the most misunderstood and trivialized area of software, because it is, in fact, not linear thinking. It's not about anecdotes, notes, lists of rules to follow. It's not something you learn in a weekend. And it is not something that is just an add-on to your knowledge, okay? It's all about first principles, okay? No matter with all the books and lists of tips and rules and techniques, everything goes back to first principles, okay? Where is the code or system spending its time? Think of that, you look at this little yin and yang diagram, it's all about where's the time being spent. Does something get called too many times? Does something get called once and take too long? It's all kind of a fractal expansion of that concept, if you will. The process, think of it like pruning a tree. Okay, if you need to prune a large tree because it's blocking a window or blocking your view or something, the tool you start with is not a pair of scissors. And you don't cut one leaf at a time. You've got to look for big branches. Okay, the idea is you've got to eliminate big parts of the tree first, and then when the tree doesn't look so good, after you've cut this big branch off, then scissors are for fine tuning, okay? That is the way to think of the process. So the paper, which I'm sure, everybody did your homework and read it, right, before you came to the session. It's intended to be a survey of various topics, not a single cohesive case study, just so you understand that. There are 17 commonly misunderstood concepts, ubiquitous mistakes in analysis that we'll examine. We use two devices to do that. One is analogy and metaphor for the non-technical world, like I said. The other is mini case studies, which today in this presentation, because of time constraints, and we have an hour, not so much. I touch on a couple of the case studies, on a couple of the major, the punchlines from those case studies toward the end, but the paper has more of the details of that. Now the case studies are based on, and they are from the world of Oracle's J.D. Edwards Enterprise One ERP system. However, I really refer to that as such very little. The concepts here are intended to be applicable to any software system, okay? The paper does have more details. The way to look at it is that if you ever know anything about the diamond mining industry, okay, you might go a whole career mining diamonds without ever seeing a diamond. You have a train car full of rubble, and then it's all about finding the, one or two diamonds that might be in that pile of rubble. That's kind of what a presentation like this is all about. There might be something there that helps you do your job better, or solve that particular type of problem. It's also billed as a beginner session, if you will, and it is. These are basic concepts. However, you'd be surprised how many advanced people, okay, don't understand these concepts. Advanced meaning they're advanced developers, advanced QA, DBAs, whatever, but basic software engineering is a holistic type concept that is not understood by too many people. So here are the concepts we'll quickly run through in survey fashion, if you will. The first one, performance engineering is a distinct discipline, okay? An ear, nose, and throat doctor, okay, you don't go out and take a weekend class to become a heart transplant doctor, okay? You don't add that to your list of skills, okay? Same thing as a plastic surgeon, highly skilled, requires years of residency and all kinds of board certification and training and whatnot, but you can't go out and do arthroscopic knee surgery just because you've gone out and taken some extra class to enrich your professional skills or whatever. In terms of Venn diagrams, they're both doctors, right? Okay, but you'd have two circles, then there'd be some overlap in there, like they both can hopefully diagnose a measles rash. You know, they both can do basic doctor type of things, take your temperature and things like that, but, you know, arthroscopic surgery, plastic surgery, different things, okay? It's the same way with software performance, okay? You get distinct career paths anybody recognizes, you know, DBA, network admin, system admin, C programming, Java programming. Well, in my opinion, the title of performance engineer is one of those, even though outside of the CMG world and in the software world in general, people don't really have a concept of that, okay? People have a concept of performance as something, well, Chris, can you give me the top 10 performance things to look for in the code? What are the top things I should be worried about? Well, again, it's not like learning your times tables, okay? It's not something you learn in a weekend. My 10-year-old is learning his timetables, right? You just memorize them. You come up with tricks, whatever, but you better know what 7 times 8, 9 times 7. You know, my 7-year-old is learning sight words. There's some words you don't sound out, really, you just gotta know. And, they, I don't know, whatever. You know, there's about a couple of dozen of them we're trying to get him to learn. It's not like that. It's about grasping first principles, okay? One good quote on this is by this person. I know I'll butcher his name if I say it, but he's the head of a company called Headstrong. He says, what's the critical requisite for a performance engineer? Somebody who asks a lot of questions. That if you're trying to solve a problem for a customer, sometimes they'll be telling you the wrong problem, okay? That, well, gee whiz, my database needs tuning. You know, well, maybe it's not the database needs tuning. The real problem is somewhere 7 levels up, some user hit an OK button and everything went too slow. They then made a series of assumptions thinking that you need to fix something in the database. You need to question even that. So you need to say, okay, what is slow? And that gets into problem definition, which we'll get into next. But again, I don't ever assume that I've been given the information in the correct way or that the problem has been defined correctly. I ask questions. You know why I ask questions? Because like Dr. House says, everybody lies, okay? Everybody thinks they know what they're talking about, but they're not really accurate. Second on the agenda, tools are the opium of the developer. How many people think you need to do performance? You go get a tool, right? Well, you don't learn to be a surgeon just because you learned how to use a bone saw and a scalpel. I mean, let's hope not, okay? Just because you know how to use a circular saw and a nail gun, anybody can read the manual, maybe learn how to cut a straight angle with a saw. That doesn't mean you know the concepts of how to build and frame a house, of how and where to set a foundation, of what to do first, the foundation, the plumbing, the electricity in the right order, how to hang sheetrock. You know, it's a systems thing, right? Building a house is more than using the tools. The tools are necessary, otherwise it'll take you forever to build a house if you're just doing it with hand tools. You've got to learn the latest and greatest tools and whatnot, but it's not the same as learning to build a house. Same thing with tools in the world of performance. They give people the illusion that they're accomplishing something just because they generated a tool that spits out data, right? So if you give somebody a tutorial or send them to a class to learn how to use Visual Quantify, that doesn't mean they can analyze performance. It means they can generate data. And just because you hand tools to a bunch of developers doesn't mean that you've given them training as performance engineers, okay? Tools are all the same thing, okay? What they do is they give answers to meaningful, well-formed questions concerning a well-defined problem. By the way, every time I put one of these light bulbs up here, kind of that's something that if I were taking notes, I would take that down as a note, as an important, takeaway, if you will. Okay? Tools give you answers, but what about the question? Anybody ever see The Hitchhiker's Guide to the Galaxy? Do you remember the answer is 42? I mean, that's the meaning of the universe, right? Well, 42 doesn't mean anything unless I know what the question is, right? I mean, the output data is something you have to interpret and analyze, and that's done by skilled individuals. Just like radiologists do with MRIs, right? My son, who was on the baseball, the Little League I was coaching, got drilled right in the eye with a baseball this summer. Ended his season a little bit, in pretty abrupt of a manner. Ended up detaching his retina. It all ended well. They've got laser surgery, they can fix that and whatnot. But they had to do an MRI to make sure he didn't break an orbital bone, right? So the MRI is just a picture, right? Anybody can read a picture, right? Well, they give you a little disc to take home, when you go have these images taken. Then you take the disc to your doctor. You sneakernet it over to your own doctor, and he looks at it and says, okay, the problem is there. Looks like he's okay there. I looked at those pictures, because naturally, being an engineer, I put this disc in and go, let's see what these pictures look like. I couldn't make heads or tails of it. I can't tell whether there's some hairline fracture, where, or even what I'm looking at. Just because it's data doesn't mean that any old, Joe Schmo, who doesn't have background in training can interpret it properly, okay? You need specialists. Next, moving along, problem definition, which could be the most important of all of these. If you don't know where you're going, chances are you'll end up someplace else. Now, kind of strange that a Red Sox fan would ever have a New York Yankee on a slide, okay, but I hate teams, but I'm a fan of players. Yogi Berra was a great one on and off the field, some of the things he said. And by the way, he once said, geez, I never said all the things I said, was one of the things, but that NY looks a lot like a swastika, don't you think? Any event, the importance of problem definition in software is that it has to be crisp and it has to be precise. Otherwise, if you guess at the problem definition, you're going to be guessing at the solution. I don't have any spells or chicken bones that I can wave over a machine or a piece of software that resolve the issue. Okay? And when people define problems in the area of performance, they tend to have problems that they don't have if the problem is functional, right? I mean, what we see is a lot of weasel words. Okay? Things like across the board, that's my favorite one. Just so you know, if anybody has J.D. Edwards at their shop and you call in for a performance problem and the first level support can't help it, can't solve it, it's probably going to come to me. And if it contains these 3 magic words across the board, that's a great way to get me to ignore it. Okay? These are actual examples here of actual people thinking that they were defining a problem. Oh, it's broken across the board, right? It's slow across the board. Well, if you've got a problem saying sales order entry is broken, so what? What does that mean? Which part of the app is broken? It's a complex app, okay? It's got all these moving parts. It's got OK buttons. It's got tabs. It's got grids. It's got menus, okay? It's a long process to enter a sales order. Which part of that is slow or slower than usual? If you don't have a problem definition, then you're in a rabbit hole, okay? So like my mother always said, ask a silly question, then I'll give you a silly answer. And my solution for across-the-board performance problems, that configuration setting right there. Go faster equals on, right up there with bugs equals off, right? That's kind of the answer you'll get if you put across-the-board into things. So again, just specifying an app is slow is not a problem definition, okay? Rigorously defining the problem comes before anything else. Collecting logs, getting data. You don't know what you're getting data about unless you know what the problem is, okay? You got to have a goal or a target in that definition, okay, for one. I got to know, am I off by a factor of 2 or am I off by a factor of 100 or a factor of 1,000? That's going to determine my strategy. Okay, if I've got something that needs to run in a minute and it runs in 7 hours, okay, I might not go picking away at code. That's probably not the right place to start. You need to be looking more holistically. Without a problem definition, it's a little bit like fire, ready, and aim, okay? Your ready and aim aren't going to do you much good after the shot's always away. But no, A tool like sales order entry is complex. It's got find operations, detail line entries, different screens, different menus and whatnot. So what I'm saying is screenshots, pictures, because a picture, this is an example of a sales order entry app, okay, where somebody showed me the exact screen of what was going on and what they were doing. And it says here, and again, this screen, unfortunately, the aspect ratio is a little bit like in a funny mirror compared to what I'm seeing. It's a little bit of a different shape, but it says there, direct ship P4210, that is J. Edwards speak for sales order, took 20 seconds to process the line. Okay, boom, I know what that means. That means they enter a detail line, they hit tab, and it takes 20 seconds to come back. That's a problem, because if they're entering 20 lines in the sales order, that's too much of a delay, okay? I can understand that. That's precise. That defines what the problem is and why, okay? Next, moving along. More CPUs don't equal more speed. Okay, you don't make a car go faster on a one-lane road by adding 2 more lanes, okay? Assuming for a second that there's not traffic on the road, okay? If it's a one-lane country road or whatever with no traffic, I'm not going to be able to drive faster by adding more lanes, right? What it does do is allows more cars to travel. It allows scalability, as it were, to give you a hint in where we're going with the analogy. And the same thing, you can't make a single-threaded program faster by running it in a machine with more CPUs, assuming it's running, by itself for a second. A single-threaded batch program is going to use one and only one CPU, no matter how many are actually available, because you're not CPU limited if you're not using 100% of one CPU, right? Now, multiple CPUs can be used to complete the work of a single batch job, okay, in less time by scaling to multiple concurrent jobs, by dividing, say if you've got a batch program, in this case, just to use some simple pseudocode, pseudo-example type pictures, if I've got something that processes data number 1 to 199 of whatever, I can divide that into 3 jobs, each of which process 333 of whatever, and get the job done in, well, not 1/3 the time, because as you all know, I'm sure CPUs don't really scale linearly, but I might be able to get 3 jobs to complete the same work in half the time, if I've got, say, 3 CPUs. Just you put some rough numbers on it. So CPUs are about scalability, not speed. This is a common misconception, okay? People think, IT folks says, oh, we spent all this money, we got this big 28-way machine, how come this thing doesn't run faster? Well, because the big 28-way machine is so that you can run lots of processes and lots of users in those processes, okay? Not a single process faster. Performance is a top-down exercise, okay? If you take CPR, one of the first things they'll tell you, what's the first thing you do with CPR? Well, you shake the person. See if they're awake, see if they respond, make sure they're just not taking a nap, okay? You don't want to have someone get up from a nap and have you pounding on their chest and giving them mouth-to-mouth, okay? That'd be a pretty weird way to wake up, okay? What you want to do is you have a certain number of tests first before you do that. It's a little bit like I always say, doctor, I keep getting a sharp pain in my eye whenever I drink a cup of coffee. Well, one approach might be you send the coffee to the lab, you run chemical tests, you might involve an ophthalmologist to see the relationship of the caffeine to the optic nerve, whatever, or option B, take the spoon out of the cup, right? So what are the spoons in the cup for performance? Well, top-down means you start with a business problem, not a problematic piece of code. You need to talk to the people that reported the problem. Those are the users, the people that could spell SQL if you spotted them the S and the Q, right? The people whose job it is to enter sales orders or to, run a journal entry program, or whatever else. You only know one thing is for certain, okay? And that's that there's a perceived performance problem. You start there, not assuming that you've got to rip into code. That means you need what's called an operation profile, starting with your problem definition, okay? I got my problem definition, something is slow, and then, how is the program used? Okay, you need the exact use case. You need all the input parameters, all the configuration details, number of concurrent users, exact specs of the machines being used, okay? Different types of software. We're going to have a little bit different twist on this, but the concept is still the same. You create a detailed description of exactly how the software is used. And what I found is the thought process involved in this first step can sometimes lead you directly to answers. Ever have that happen? Sometimes you're going through and you're trying to get your arms around the problem, whether you know it or not, you're defining the problem, and the answer just comes right out at you, okay? Because you are thinking through things. In my experience, most of the problems that I solve, because that is a good part of what I do, I help solve problems with live software that is going either too slow compared to perceived, requirements or compared to something they used before. Most of them are due to configuration type issues, not that the code needs to be changed, okay? Especially for a relatively mature product, and the J.D. Edwards product has been around for about 15 years. For the most part, wholesale changes in the code, don't really need to be made to solve most of these problems. Moving along to benchmarks are for hardware, not software, okay? You can't predict or guarantee your salary just by looking at statistics from a given profession. Like if someone says, oh, what's the average lawyer make? Well, I've got a friend back home in Colorado. He was a prosecutor for a small rural county. He made about $30,000 a year. Okay? On the other hand, there are lawyers that work for a hotshot, big defense firms that can make 7 figures a year, right? There's a very wide range. There's other people that do pro bono work, that do give legal services for free or whatever. If you're a baseball player, well, coach my son's little league team. I do that for the love of the game, so to speak, not because you get any payment. If you're coaching the big leagues, you can make 7 figures. The answer is it depends. You need more information. What does the average lawyer make? Doesn't make any sense. The same thing with these benchmarks for software. They are not performance tests. Okay? Every installation is different. And just like 2 snowflakes are different. At best, when you get these benchmarks that vendors produce, they should be looked at as smoke tests, okay? Well, if things don't work with very basic scenarios, then more complicated ones certainly aren't going to. There's no 100% guarantees of performance, and there's no 100% accurate benchmark of your system other than the one you do against your system. Okay, against your data in your live environment. That's what benchmarks all about. And don't forget benchmarks generally, when the hardware vendors set them up, at least in our space, in the J.D. Edwards space, you find they use happy path type scenarios that a lot of advanced features like pricing, advanced transportation and whatnot are not turned on. Why? Because it's all about driving as many transactions as they can through the hardware. Okay, and the software is secondary toward how many transactions can the hardware tolerate. And oftentimes these are high watermarks. You got to figure if someone says they can bench press 300 pounds, well, that's not the same thing as saying they can carry a 300-pound sofa up the stairs at your house, so don't ask them, right? A bench press is something like a benchmark. It is something you do under a certain very controlled, specified set of conditions. You're on your back. You're going to take a weight. You're going to bring it down to your chest and push it back up once and put it back, right? It's a different thing than using the number 300 to say that you can carry something or do something else. And I bet I'm the only presentation that has a Chris Farley quote, okay, on any of their slides this week. And I've been paying attention. Nobody else has one either. So it's all about guarantees and all about, what a guarantee really means. I mean, it means the guarantee fairy is going to leave a quarter under your pillow or something. So anyway, moving along, sample size is critical. Anybody here a baseball fan? Anybody here follows good? Software people aren't baseball, you just, Any event, baseball is a game of statistics, okay? It's all about statistics, more than any other sport, even football, because there are fewer games in football, right? Baseball, I have 162 games. What this quote basically says is, if you've got somebody who goes 0 for 4 in one game, you can't assume that they're going to get no hits for the entire year in 162 games. By the same token, just because they go 3 for 4 in one game doesn't mean their average will be 750 over it. You need more than 4 or 5 games. You need more than 10 games. You probably need 30 or 40 games to really not only account for them having a bad day at the plate, or maybe they didn't get a hit because they took intentional walks, got sacrificed flies, all kinds of things go into it. And then you've got to account for hitting slumps and whatnot. You've got to account for all of these things. And baseball is all about the fact that the larger pile of data you have to work with, the more confidently you can draw conclusions about what it means, okay? And a common miscalculation in the software world is extrapolation. Okay, software is not linearly. It doesn't behave linear. It doesn't behave in that fashion, despite human attempts to impose physical world linear restrictions on it. So, for example, you might try to extrapolate results from a very small data set. You can't reliably profile, for example, a batch job, what its behavior is against 1 million records by running it against one record and extrapolating 1 million times. That doesn't work. Okay? If you take a look at these couple of charts here, and this is a graph of just a very almost pseudocodish type of a graph of, say it's a batch program, and on the x-axis is time, and you can see if I just have two sections of code, say, one that does something, section 1, in a short period of time, and then one that does something very different in section 2, and the behavior of the program changes in section 2, and maybe this is where the problem is. Maybe this is why the program is taking so long. But if I don't know that, okay, and I only sample a very small part of section 1, I'm not going to be sampling the part of the code that's really causing it to run 10 hours. I'm only sampling it during part of the first hour that doesn't contain the problem. I'll never see what's going on in here because I only took this first chunk, the first few minutes or whatever of the run. The same thing that could happen, suppose in this other picture is from a different perspective. Maybe the code is uniform for this batch program. Maybe it's one big while loop or something, but the data changes, okay? Maybe it runs over different ranges of data as time goes by, or maybe something about the data changes. Maybe I hit some internal threshold, all of a sudden I start running longer. But something bad doesn't happen until a little ways into the code, and if I sample at the beginning, I'll never see that, okay? Basically, never test against one of anything is the rule. You've got to account for outliers. You've got to account for statistical averages, things like that. So truncation is not sampling, is the thing. Sampling only the beginning or part of a long-running program won't capture problematic behavior. Like Mark Twain said, there's 3 types of lies: lies, damn lies, and statistics. Statistics can be manipulated to say anything you want, okay? A more precise picture of a J.D. Edwards batch job is here. This is CPU over time in the x-axis. You can see the program is doing something very different here than it is here, okay, just by the CPU profile. You don't want to sample just here. You can tell intuitively that that's the case because I'm not capturing everything this UBE is doing, okay?